All right, so a question was posed to me in the back of the main office by the copier, which was, why does A equals P times the quantity 1 plus R over N all to the NT turn into A equals PER to the T as N gets really huge? Meaning, as you compound interest continuously, why do we switch from using the first formula, the one with the R over N to the NT, to the second formula, the A equals PE to the RT? So, like most of the algebraic formulae that you're going to see, the roots are in calculus, and in order to prove it, you're going to need some calculus, which you probably don't have if you're just learning this formula, but I'm going to walk you through it anyway. I will say that you can logic through some of it using a calculator. So I have my calculator pulled up here. Now, what you can figure out on a calculator is, on a calculator, you can figure out that as you get, we'll use x in this case, because we're going to use x on the calculator, as x values get huge, 1 plus 1 over x to the x is going to approach e, right? And you'll be able to see this if you put this in as your y in your calculator. You can actually figure it out by doing table set. So if I go to table set and I start my e values at, like, I don't know, let's start at 10. And then let's not my e values, my x values rather. And then let's go by tens. Let's just see what happens, right? And then if I go to table, so I go to table, you're going to see that the values get closer and closer, right? See, they're 2.6, 2.7, 2. Whatever, right? They're going to get closer and closer to e, and you can sort of start to see that happening, right? They're 2.71, et cetera, et cetera. So if I go out of this for a second, I pick e. So you'll see that e, right? So e is approximately, like, if it helps your brain. I always think of e as 3-ish, just like I think of pi as 3-ish, because they're irrational numbers, so they don't actually have a value other than the letter that is assigned to them. They go on forever. They don't have a terminating value. But what you'll see if I go back to my table is that these numbers are getting closer and closer to that 2.718, et cetera, et cetera, et cetera. In fact, if I go back to table set and I start bigger, let's say I start at like 100 and I go by hundreds, right? So I start at x as 100 and I go by hundreds and I go back to my table. You'll see that these values are getting very, very close, right? And so I'm getting really close to that 2.718, et cetera, as I get, but this isn't anywhere near infinity, right? Infinity is an impossibly large number, and 4,200 is not impossibly large. It's just like an average old large number, right? So if I go to table set and I pick something much larger, let's say I go to pick 1,000,000. 1, 2, 3, 4, 5, 6, and let's say I make my let's see, we've got 1,000,000 as my change in the table as well. Oh, well, look, now they're very clearly all approaching that same value, right? And they get closer and closer. You can see those final digits are changing, but we're locked in at the first at least 5 digits after the decimal, being very, very close to e. Okay, so we can see that using a calculator. You could see that if you plugged in a ton of different numbers. I'm just too lazy to plug in a ton of different numbers. So let's do the calculus for where this comes from. All right, so this is going to rely on a couple things. It's going to rely on an understanding of how we deal with limits. So there's a thing called L'Hopital's that you're going to learn in 4.7 of AP Calc that basically says if we have a limit as x goes to some letter, could be a, could be infinity, could be anything. If I have a limit and it's what's called an indeterminate form, like it's 0 over 0 or infinity over infinity, or it's a 0 times an infinity, any of these indeterminate forms, that I can essentially say that this is equal to what would happen if I took the same limit, but of the derivatives of those two functions. And again, if you're not in calculus, you're like, this is gibberish, Hogan, and that's fair. But we're going to use L'Hopital's. So essentially what I need to show, since I have this a equals p 1 plus r over n to the nt, and I'm trying to show why it becomes p e to the rt, it seems to me that I need to show that this piece and this piece are the same. So the question is, for infinitely large n, how do I get this? Well, in order to figure that out, I'm actually going to use x's, not n's, because to use L'Hopital's, we need to use things that are continuous, and things that have n's are by default not continuous because they're discrete math, they're all whole numbered values. So we're going to see what the limit as x approaches infinity of 1 plus r over x to the x's. So I'm using x's instead of n's. Well, the problem here, so I want this to be some value. I'm just going to call this value L. I want to find the value L. The problem I run into here is that when I plug in infinity, which I'm not really supposed to do, but logically when I plug in infinity, I'm going to get a 1, right? I'm going to get a 1 plus a 0 to the infinity, right? So I'm going to get a 1 to the infinity, and 1 to the infinity is another one of those indeterminate forms. So what I'm going to do is I'm going to go ahead and take the natural log of both sides. So I'm going to go ahead and say the limit as x approaches infinity. Oh, and there's a chance that you don't know natural logs yet too while you're watching this. It really depends on what class you're in. But I'm going to take the natural log of both sides, right? And then what the natural log allows me to do is it allows me to drop exponents down. So I'm going to get that this is the limit as x approaches infinity of an x times the natural log of a 1 plus r over x. And that equals the natural log of L. Well, the problem we're going to run into here is if I plug in infinities, I'm going to end up getting an infinity times a natural log of 1, which is an infinity times a 0, which is, again, one of those indeterminate forms. But in order to do L'Hopital's, you'll notice that I need to have a function over another function. So what I'm going to do is I'm going to rewrite this limit as x approaches infinity of x times the natural log of 1 plus r over x, which, as you'll recall, is equal to the natural log of the quantity we want. I'm going to rewrite this as a natural log, or sorry, a limit of, as x approaches infinity, of a natural log of this stuff. And instead of multiplying by x, I'm going to divide by 1 over x, because that would be the same thing. And when I plug in now, right, the trick is that in order to do L'Hopital's, if we hop back up here, I need it to look like one of this, or one of these. I need it to look like one of these first. So, so while this is another indeterminate form, I need to rewrite it so it looks like one of these. So I now have a situation where if I plug in infinity, I get a natural log of 1, which is a 0, over a 0. So 0 over 0 means that I'm okay to do L'Hopital's, which I frequently write in my notes as just L-hop because I'm lazy. So I'm okay to do L'Hopital's. Well, now this is where we have to do some more calculus. So the limit as x approaches infinity of the natural log of 1 plus r over x divided by 1 over x, which we know is the same as the natural log of L, I'm now allowed to differentiate to do L'Hopital's. And so when I differentiate to do L'Hopital's, I'm going to get, again, I understand that you don't know derivatives yet because you're watching this video and you're not in calculus, but I'm going to get 1 over the stuff times the derivative of this stuff, which again, you don't know how to do yet. That's the top. And on the bottom, I'm going to get 1 over a negative 1 over an x squared. Well, now if I clean this up a little bit, I'm actually able to clean this up and cancel a negative 1 over x squared. So this thing is going to cancel with this thing, but not the r, because this is the same as an r times a negative 1 over x squared, so I can cancel those things. What this means is I get that this is the limit as x approaches infinity of a 1 over 1 plus r over x times an r. Well, now when I plug in infinity, I'm going to get that this is a 1 over a 1 plus 0 times an r. Well, that's a 1 times an r, which is just an r. And recall that this whole thing at the beginning, right, this whole limit at the beginning as x approaches infinity of 1 plus 1 over x to the x, we had said that was L. When we took the natural log of both sides, we then said that all that stuff that we just did, all of that work that we just did was equal to the natural log of L. Well, we got that this limit is r, so r equals the natural log of L. To solve a natural log to solve for L, we would exponentiate with e, so I would get that this limit is equal to e to the r. So back way at the beginning, I said that we were trying to show that 1 plus r over, in this case, an x instead of an n, all to the x would be the same value as e to the r, and it turns out it is. So using calculus, we can replace, so this formula where we have p, 1 plus r over n to the nt, as n gets infinitely large, this becomes p e to the rt, okay? And we see that again by doing the limit to show that this value becomes this for infinitely large values of n. And again, that's calculus, not pre-calc, but that is one way that you can figure it out.